Okay. Whoa. It's very loud for us in here, but I don't think there's anything I can do about that. Maybe it's just that this room is smaller than Flenchy. Okay, so this is revision seminar for Maths 1B on linear transformations, and afterwards we'll have a request session as I've been doing all day. So and we will zoom in. Okay, so I'm going to give you my version of what I think about linear transformations. So yesterday, and you've been learning about multivariable functions that take several variables in and spit a single number out. So you've seen things like it's something like that, for example. And what this does, this is not part of linear transformations, but what this does is we've got a function f and it takes R2, numbers 2 dimensions, and produces a single number as its answer. And that's what you've been working with multivariable calculus. Well, linear transformations takes lists of numbers in and produces a vector out. It doesn't just produce a single number, it produces a vector of numbers as the outcome. And it is actually possible to have even more creative functions that have squares and all sorts of things in it, but linear transformations are the simplest kind of multivariable functions, and so that's what you study in Maths 1B. And not only that, linear transformations are deeply connected to subspaces, and you've been learning about that in Maths 1A and Maths 1B, and so it's useful to know about them. So you can use stuff that you learn in Maths 1A to do something new, which is one of the reasons you have them. So a linear transformation is a function f that goes from Rn to Rm, or possibly m to n, but it doesn't really matter. So the idea is it takes vectors in, and the answers that it spits out are also vectors. So far you've only been used to things that take numbers in and spit numbers out, or take vectors in and spit a single number out, and now we have something that spits vectors out as its answers as well. But while there are many possible things that you could do with that, a linear transformation isn't just any old function that goes from Rn to Rm. It's a function that is linear, in the sense that if you have a formula in each coordinate, they all have to be linear equations. And it has these properties, such that for any u and v in Rn and any c in R, we have that f of u plus v is f of u plus f of v, and f of cu is c f of u. So you can have whole lots of things, but linear transformations have these two special properties. And that's what we call a function being linear. And there are all sorts of linear functions from one place to another. And linear just means that you can treat it as if it was just multiplying by the number f, because you're just expanding out the brackets, right? You can bring the f in next to both of them to produce that, and you can bring the c out. It's the same as the rules for summation notation. Okay, so being a linear transformation is having that sort of property of being roughly the same as just multiplying by something. Okay, that's the definition. Awesome. So being functions, things that we might be interested in about a function are its domain and its range. So as I always do with these seminars, just need to say at this point, I may not cover everything, and because I'll just do whatever's in my head, but you know, it's my job to put the disclaimer at the front that says if I don't cover everything, you still have to study everything else. Right, so we might be interested in the domain and the range, right? So the domain is Rn, because a linear transformation is defined so that there is no problem, you can do it on any vector, okay? So you don't have to do anything where you look to see where it's defined and restrict the domain to something where it's actually defined. So it's not like root x where you can only put positive things in. So just so that you know, so f sends Rn to Rm. This is the domain. And the range is the set of all the answers that come out. It's the same as the range for ordinary functions. The answers happen to be vectors. So the range isn't equal to this necessarily, it's just contained in there somewhere. So range is in here. Okay? And the range of f is the set of all things that are f of something, which is the same as the definition of range for any function whatsoever. So to find the range, you technically have to take every vector in Rn and do f on it, and what's produced is the range. Yes?
So the range is formally a subspace of Rn, since although it may not have dimension, its dimension is less than m.
Yep. No, it could actually be equal to m. So I'm getting to that. So at the moment, the range is a set. You can define the range as just a set of vectors. But because of the way linear transformations are defined, and because these are extremely reminiscent of the laws for subspaces, the range has to be a subspace. And so that makes finding ranges for linear transformations easy in the sense that it was really hard to find the range for an ordinary function, but because you know it's a subspace, finding the range for a linear transformation is much easier. Okay. So the next thing I want to talk about is what linear transformations do. Before I start talking about how to find the range and the kernel and those sorts of things, I want to talk about what they do to vectors. And you need to find a new way of thinking about functions that you weren't doing before. So with ordinary functions, something like y equals x squared, which is not a linear transformation, but with ordinary functions like y equals x squared, you were used to thinking of them as something like this, right? And then you were used to saying, well, here's the domain here, and here is the range here. You were used to doing that. And we can't do that with linear transformations because, firstly, we can't draw graphs of them because it might be from R3 to R2. So you can't draw a graph of a linear transformation necessarily. So we need to think of a way of thinking about functions that's going to match with that. So we're going to think about functions as before and after. So this function, what it does is it takes numbers here on the x-axis and produces its answers here on the y-axis. So something like that. You take a number here, via the function you go to the y-axis. So we can have a before picture, which is the x-axis, and we can have an after picture, which is the y-axis. And my domain was all of this, but my range was only this bit here. And if you pick any point anywhere on this line, you can figure out where it ends up afterwards. So this point here, at say -2, afterwards is over here at +4. And this point here at +2 also ends up at +4 afterwards. So A, B, there's the answers for A and B. And this point here for 1 ends up here at 1. And this point here at a half ends up here at a quarter. And so things are not in the same arrangement as they were before when you do them after. It's useful to think about that. So what squared does is things that are bunched up here, when you square them, they get all spread out afterwards. So we need to start thinking about what functions do to objects. And so we have a collection of dots. What happens to it after we do the function? That's how to think about linear transformations. So for linear transformations, for example, you might have something like can't do squares. fxy is x plus y minus x. So this function goes from R2 to R2. So here there's 2 coordinates here, and there's 2 coordinates here, like that. And so we need a before picture and an after picture for that. So we can have a before and an after. And we can draw points and see where they go. So this point 0, 0, if I put 0, 0 into the formula, I get 0, 0, which always happens with a linear transformation. And this point 1, 0, when I put it into the formula, I get 1 minus 1. And this point 0, 1, when I put it into the transformation, it gives me 1, 0. And so every point here has a result over here. And you can imagine that if you had a decent way of looking at it, you could see that maybe the linear transformation would rotate points, or maybe it would scrunch them together, or maybe it would turn them in the opposite direction, or whatever it might do. Okay? So that's a useful way of thinking about it. Okay, so now I can start talking about range. And the usefulness of the before and after is that I can think this can be any dimensions and this can be any dimensions too. So I can draw it in 3D and it might end up on a 2-dimensional thing. Or it might be from 2D and it might end up in a 1-dimensional place. So just as another example, that was an example. f of xy is 2x minus y. It's just an ordinary multivariable function. So this is something you could do derivatives and all sorts of things with this, but we're thinking of it as a linear transformation. So f is sending R2 here, and the answer only has one coordinate. It's just a single number, so there it goes to R1. Okay, so we have a before, and we have an after. Oop, there is no y-axis in the after because it's just a single number line. So the after is just a single line with a 0 in the center. So here we have 0, 0. And as always, that will, when I put it into the formula, I'll get 2 times 0 minus 0, which is 0. And here I have the point 1, 0. And when I put it into the formula, I get 2 times 1 minus 1. So this is coming to the point 1. And here I have the point 0, 1. Sorry, it's 2. Crap. This is the point 2. Because it's 2 times 1 minus 0, isn't it? Okay. And here I have the point 0, 1, which goes to minus 1. Which is actually here, sorry. And so every point, this entire plane is being squashed onto this line. Okay? What's going to happen is that there will be a place where all of the points in a certain spot, on a certain line somewhere, will go to the same place. Okay, so because we've got 2 dimension here and only 1 dimension here, we have to lose a whole dimension. So there must be a whole lot of points that end up in the same place, because they can't all go to different places because there's not enough room. So we can find, for example, all of the points in here that end up at 0. So let's just find some of them. So obviously 0 ends up at 0. And let's see, the point 1, 2 would also end up at 0. That would end up at 0. So it'll end up here as well. Okay, and the point a half 1 would also end up at 0. And the point minus 1, minus 2 would also end up at 0. And in fact, anything on this line, that entire line, when you do the linear transformation, will end up here at 0. That's what we mean by the kernel. The kernel is the set of points here, which when I do the linear transformation ends up at 0 afterwards. It could end up at the 0 vector, but it ends up at the origin of your new place. And what ends up happening is that you end up cutting up the entire of this space into slices that are the same shape as the kernel. So this point here, there'll be another line here that's parallel to that one, and all of those will end up where this one ends up. And there'll be a line here that's parallel to the kernel, and all of them will end up there. Okay? That's how linear transformations work. You end up slicing in the beginning space, the before space, the domain, into slices, and each slice goes to the same point. Okay, and all of those slices are the same shape as the kernel, they're just in different spots. Now your lecturer wouldn't have told you that, but I find it very useful, because what I've done is I've said, okay, I've got 2 dimensions here and I need to produce 1 dimension afterwards. Well, if I just cut it into lines, now I've sort of got this concept of each line represents 1 point on this line. I've flipped them around the other way, of course, because this one that's up is ended up here on the back, on the left-hand side. So everything's round the wrong way, but that's okay. Linear transformations are allowed to flip stuff. So it should be possible to find a line that you can draw somewhere that would match where it ends up on the new x-axis afterwards. Cool. That's what it looks like. And so you can do it in 3D as well. You can do 3D to 2D or 3D to 3D or 2D to 2D, and it will turn out that there's a before and an after, and you may not be able to cover the whole of the after space. So here's one more example before I get to saying the definition. So here's another linear transformation that goes from R2 to R2. I'm choosing R2 so that I can draw it on the page. Don't like trying to draw R3 on my page. And so I can draw my before and after. Okay. My pencils are going blunt, and my sharpener doesn't fit the fat pencils. So the origin here, 0, 0, as always, will end up at 0, 0 afterwards. That's always true for a linear transformation. Okay, and what about the point 1, 0? So I put 1, 0 into the formula, I get 1 minus 0, 0, so that's in the same place as it used to be. Yep. Okay, and what about the point 0, 1? That ends up at here, minus 1, 0. Only it's here. Minus 1, 0. Okay, cool. So this entire, well, let's just think about the y-axis. If I picked another point on the y-axis, it would still end up on the x-axis afterwards. In fact, no matter which point I pick, the second coordinate's always 0. So the only things I can possibly produce are afterwards. Yep?
So just with this example, could we say that that's a linear transformation to 2 dimensions to 1 dimension because the y will always be 0?
Yep, someone's just said, for those who are listening, can we think of this as a transformation that goes from 2 dimensions to 1 dimensions? The answer is yes and no. So the range is 1-dimensional. Okay, so this object here, that line, is a 1-dimensional object, but it's still producing points that are in R2. Those points still have 2 coordinates, it's just that one of them is 0. So technically, no, it's not going to 1 dimensions, but the object that it's producing is a 1-dimensional object. Yeah. So here's my range here. I can only produce these. Okay? So my range is the x-axis, all the things that are something 0. Now, because I have gone to 1 dimensions, I've taken a 2-dimensional object and the answer afterwards is a 1-dimensional object, so I've lost a whole dimension. So that means that a whole lot of points must all end up at the same place because I haven't got enough room. So there must be over here a whole lot of points that end up at 0. And those points will make a line. And, well, I can think that out. In order to be 0, it must be x minus y equals 0. So if f of x, y equals 0, 0, that means that x minus y is 0, which means that y equals x. So this line here, that line necessarily, all of those points, no matter what they are, end up here. And every single line that's parallel to that will end up at one of those points. So this line here, all of those points will end up there. And this line here, all of those points will end up there. So you can see why it ends up here, because its matching point over here on the x-axis doesn't move. So what we've really done is we've just copied the x-axis exactly as it was, and everything that was on that line of slope 1 is going to the same place that that point goes. So we've really just sliced this up into pieces and said, actually, we're just going to produce those points afterwards. Okay? Right. They don't talk to you about these things here. That's called a pre-image, they call it, or a codomain, if you like. But this thing here, that blue bit that produces the origin afterwards, is the kernel. So this thing here is the kernel. And the reason we're so interested in the kernel is that the kernel doesn't just tell us what goes to 0. If I pick any outcome point, it will tell us everything that goes there as well. Because I just have to go, well, this point ends up there. I can find all the other points that go there by just copying the kernel and putting it through that point. So in R3, the kernel could be a plane. But in that case, if it was, you would produce a 1-dimensional object in wherever it was you were going. Okay. Now that you have a picture, I needed to give you a picture so that you have something to think about. So we've got a couple of definitions. We know that the range of f is the set of things that can be written as, so we've got f sends r. Did I say n yet? So the range of f is the set of outcomes, and the kernel of f is the set of inputs that produce the 0 vector. So it's the set of vectors in Rn such that f of u is 0. Okay, so it's saying I need to pick vectors that were in the before space so that afterwards they end up at the 0 vector. That's what this says, the kernel. The range says I need to get all possible vectors here and see where they go and see what I produce afterwards. That's what the range is. So the range lives in the after space and the kernel lives in the before space. Okay, but they are both subspaces. So there's a theorem somewhere that says both of them are subspaces. necessarily the kernel does go through the origin because the origin goes to 0, and the range certainly goes through the origin because you can produce 0 as an answer, but all of the other rules for subspaces also apply. Awesome. So that means being subspaces, the only thing you need in order to describe the range is a set of vectors to be its basis, and the same as the kernel. So even though ranges with ordinary multivariable functions can be very difficult to describe, and so can domains, for linear transformations it's very easy in inverted commas, because you just need basis for them. So they're subspaces, so they each have a basis. Okay, and you can find that basis by simply solving you can find the basis for the kernel by simply solving this equation. So I say simply, but that's what you need to do. Finding a basis for the range is a little harder, okay? As is, ranges are always harder. The kernel is part of the domain. Domains are always easier than ranges, and that's still the truth now. So as an example, f of x, y, z, I'm going from R3 this time. And I'm ending up in R4. You can go from a small space to a bigger space. Okay? So, the range is the set of all vectors that come out. These are the outcomes. So that's f of x, y, z. Well, let's think about that. I know it's a subspace and I want to write it with a basis, so all I need to do is write it as the span of something and that will do the trick. So I'm going to rewrite this in terms of the x and the y and the z. So I've got x, 1, 0, minus 1, 0. And I've got y plus z in this coordinate. So normally you'd go, well, it's y plus 0, 1, 0, 0 plus z times 0, 1, 0, 0. Okay, so I've just, for each of the variables, I've given a vector that tells me where those variables are in the formula. And you can see that these two are the same one anyway, so I'll just combine them together. So I've really got a linear combination of this vector and that vector. And as long as those vectors are independent, it must be the basis, which they are because this one has a 0 in that spot and this one doesn't. So we have, therefore, the basis for the range is those two vectors. Okay? So if it's written in this form, finding a basis of the range is actually quite straightforward. Because you know that a basis is designed to write something as the span, so you want to rewrite it as a linear combinations of stuff. The kernel of f is the set of x's and y's and z's such that the answer comes out to 0. And that has 4 coordinates there, which means that we want to solve this equation. Like that. We want to solve which of these answers comes out to 0. And we can just go, well, x has to be 0 from the first coordinate, and from the third coordinate as well, and y plus z has to be 0. We just want to solve those equations that come up. So that means that technically we're actually going to be solving a matrix at this point. But at the moment, it's not actually completely necessary because we know x is 0, and we know that y is equal to minus z. So we can write everything in terms of that. So in fact, x, y, z is equal to 0 minus z, z, which is z, 0, minus 1, 1. And so therefore I've written it as a span. So therefore the kernel of f, a basis for the kernel of f is 0, minus 1, 1. Okay, yay. Okay, that's fine. There is another way, and I'm getting to that, and your way that you're probably most used to. But I wanted to show you that it's possible without knowing anything but the definition of what a linear transformation is. Okay, let's just think about this, because this is really important. The dimension of my range is 2. It has 2 vectors in its basis. So my range is a plane. It's in 4-dimensional space, but it's a 2-dimensional object. So I've gone from 3 dimensions to a 2-dimensional object. That 2-dimensional object is in a bigger space, but that's fine. So I've had produced 2 dimensions as my outcome. I started with 3 dimensions to begin with. This was a 3 dimensions to 4 dimensions. There were 3 dimensions to begin with, and there were 2 dimensions as the outcome. So I have to have lost a dimension along the way, and that lost dimension is in the kernel. So we have 2 dimensions in the outcome, and 1 dimension left behind in the kernel, and that leaves you with 3 in total in the original space. So just note, f sent R3 to R4, and we know that the dimension of the range of f is 2, and the dimension of the kernel of f was 1, and so therefore, not therefore, but just note that 2 plus 1 equals 3. So that 3 that we came from is the sum of the dimensions of the range and the kernel. So the range is the dimension that we end up with afterwards, and the kernel is the amount of dimensions that we lost along the way. Right, so that means if you go from a big space into a small space, you must have some dimensions in the kernel. So if you go from R2 to R1, you have to leave at least 1 dimension behind, because you've lost a whole dimension in the new place. If you're going from R3 to R4, then you don't have to leave anything behind. You can produce a 3-dimensional object in the outcome, and your kernel can just be the 0 vector, which has dimension 0. Okay, so in my original example here, not that one, this one, the points that I can produce here are linearly, like that, those 2 points are linearly independent of each other. So I must be able to cover the whole of R2. So my range is actually 2-dimensional, which means my kernel must be just the 0 vector. The only vector that ends up here must be that one, because I'm actually able to produce 2 dimensions over here. I'm able to produce 2 vectors that are independent, so I must be able to produce everything. Okay, almost there. So, I don't know if you remember, if you saw my seminar for subspaces, I said there's a definition for what a subspace is, and then there's a list of things that you know must be subspaces. Okay, so you know that a subspace has its definition, and then it could be the span, or it could be the solutions to linear equations. They must be subspaces. Okay, the same goes for linear transformations. There is a definition of what a linear transformation is. It's a function that has these properties. But there is also something that is definitely a linear transformation, and that is something that is defined by matrix multiplication. Always, definitely, linear transformation. So, that's sort of a theorem, right? Not really a theorem, but it's a fact that if f of column vector is defined as matrix times column vector, so this is a column vector. Up till now I've been writing my vectors as rows, but in order to do matrix multiplication I would prefer them to be columns so that I can put the matrix on the left. So if my function is defined as matrix, right, by matrix multiplication, then it must be a linear transformation. And even better, every linear transformation can be written that way if you want. Okay, the fact is that this is definitely a linear transformation, and it has to be because it's basically just doing linear equations. But every linear transformation can be written with a matrix if we want. Okay? In the same way that with subspaces, the span of things is definitely a subspace. Well, in fact, every subspace can be written as the span of something, and that's what a basis is for. And it's the same deal here. Any matrix will produce a linear transformation, but every linear transformation actually has a matrix if you really want. And that matrix is called, and in fact, it's better than that. It's not just that every linear transformation can be rewritten with a matrix, and can be rewritten with a matrix in exactly one way. There's only one matrix that will make it work. There is only one. No matter if you've got a linear transformation, there is only one way to write it as a matrix multiplication. And that matrix is called the standard matrix. It's funny that it's called the standard matrix because there's only one. You might as well just call it the matrix, but there you go. That's what it's called. Okay? I think maybe it's standard because you're treating them as columns rather than rows, because it's possible to have a matrix with rows as well. Okay, so because there's only one way, if someone says find the standard matrix, if you can think of a matrix that produces that answer, it must be the answer. Find the standard matrix for this function, the one that I had before, that one there. If you can think of a matrix that works, then you can do it. So let's just look at it. We have to have a matrix here, and we have to put x, y, z as a column. And the answer that comes out must be x, y plus z minus x 0, because it has to be written as columns. So in order for the sizes of the matrices to work out, I need to have 3 columns here so that I can multiply by it like that, and I need to have 4 rows so that the answer comes out to have 4. So let's see. This first coordinate here will be produced by going that row times that column. So it has 1 x and no y's and no z's. And this second coordinate has no x's and 1 y and 1 z. And the third coordinate has minus 1 x's and no y's and no z's, and the last coordinate has nothing at all. There is my standard matrix. You just check if it works. X, 0, 0 is correct. 0, y, z, yes. Minus 1, yes, it works. Okay, so that must be the standard matrix. Since there's only one standard matrix, it must be the only standard matrix. There is another way. There is another way that is awfully clever. The awfully clever way says that, look, if I have a matrix and I want to know what the first column is, all I have to do is multiply it by 1, 0, 0. And that will tell me the first column, because these both being 0 means that everything here will be multiplied by 0. And if I want to know what the second column is, all I have to do is multiply it by 0, 1, 0. And if I want to know what the third column is, all I have to do is multiply it by 0, 0, 1. So I could just as easily have done this, or f of 1, 0, 0 is, subbing 1, 0, 0 into the formula, I get 1, 0, minus 1, 0. Awesome. And f of 0, 1, 0 is 0, 1, 0, 0. And f of 0, 0, 1 is 0, 0 plus 1. 0. And they are the 3 columns of this matrix. So, the reason why this is helpful is sometimes you don't have a formula for your linear transformation. Sometimes your linear transformation is, for example, the orthogonal projection onto a particular subspace. And while you may not have a proper formula that looks like this, you can at least figure out what the projection of 1, 0, 0 is, and the projection of 0, 1, 0, and the projection of 0, 0, 1, and therefore they must be the columns of the standard matrix. And then, once you've got a standard matrix, you don't have to do all the dot products and the stuff, because all you have to do is multiply things by the matrix. That's the reason why standard matrices are so wonderful, because while, you know, the process of you know, it's awfully magical that you can do dot products times an orthonormal basis to produce an orthogonal projection, it does take a while with all those dot products. But matrix multiplication is a little easier to do. Especially computers can be taught to do it rather quickly, especially if there's a lot of zeros. Okay, so now that we have, let's go see where we've been. We've got functions that go from Rn to Rm, and we know about the range that produces certain outcomes, and we know all the outcomes that are produced, and we know about the kernel, which is all the ones that go to 0, and we know that what will happen is that you'll split the beginning space into slices that are the same size as the kernel, and that's how you produce the finishing outcome. And we know that every linear transformation has a matrix to go with it. Well, now that we know that there is a matrix, we can just use matrices to solve all of the other problems, because we're used to using matrices by now. So now that we have a matrix, we can have this awesome thing that says that the kernel of the transformation is the same as the null space of the matrix. So the kernel of f would be the set of vectors u such that f of u is 0, which would be the same as the set of vectors u such that a times u is 0 if it does have a matrix. And that's the solutions to your matrix. And so it must be the null space of the matrix. Awesome. A bit of maths grammar. You cannot say that the linear transformation has a null space. The linear transformation has a kernel. The matrix has a null space. The kernel is a word that belongs to a linear transformation, and null space is a word that belongs to matrices. That's just grammar in maths. It's the same as there is the characteristic polynomial of a matrix, and there is the characteristic equation, and the equation is the one with the equals, and the polynomial is the one without. It's just words. No one will really care that much, but you will annoy the person who is marking your exam if you use the wrong one. And an annoyed marker is less likely to give half marks for something. So just, yeah, be clear that don't say the null space of f, because that doesn't mean anything. Say the kernel of f and the null space of a. Okay? And f is a function. It's not the same as a. A is the process by which we produce the answer. F is the whole concept. Okay, and the range of f is the set of things that could be written this way, which is the set of things that could be written this way, and when you multiply a matrix by a vector, what you're really doing is a linear combination of the columns. The set of all the linear combinations of the columns of A, which is the column space of A. So in the same way, range belongs to the transformation and column space belongs to the matrix. So that means if you do have a matrix, the quickest way to find the kernel and the range is to do row operations. So let's shift that up a bit. So what about I'll do the same one I had before, but I'll do it with the matrix instead of doing it directly, just so you can see that it comes out to the same answer. Okay, so this is in fact equal to, as columns, f of x, y, z this. Okay, so that's my standard matrix there. So in order to find the kernel, I need to solve this times this equals 0. And in order to find the column space, I need to find all the possible combinations of the columns. And so the column space is already, the column space, I already have some vectors that span the column space. All I need to do is find the ones that are linearly independent. And the kernel, well, I actually need to, I don't have, the matrix itself doesn't include the kernel. You have to add variables to produce the kernel because the kernel is here, not here. So to find both of them, I need to do row operations, and this one is particularly simple. So technically there's zeros here, but you don't need them. So I can do a single row operation to finish this off. Awesome. My new row 3 is row 3 plus row 1. And so here are my pivot columns. The original columns that they came from, they are the basis for the column space, and hence the basis for the range. Okay? So we have the original columns they came from are here. So we have, I'll get to that in a second, I'll do the kernel first. We have two pivot columns here. This one must be a free variable, and that's how we're going to find the kernel. So here we have t for that. This one here is therefore minus t, and this one here is equal to 0. Okay, so that's my kernel. So the kernel of f is the span of 0, minus 1, 1, which is the basis we got before. And the range is the span of the original columns that produced the pivot there. So the range of f is the span of these two vectors. If they were originally written as columns, you should write them as columns. But my original matrix was written as, my original formula was written as rows, so I'll keep them as rows. So, and that's, there you go, done. I can't remember anything else that's involved with linear transformations. Oh yes, I remember. Then there's this awesome question that goes like this. Okay, so there's this awesome question, whether your lecturers think is awesome anyway, that goes like this. F is a linear transformation such that f of 1, 0, 0 is 2, 3, and f of 1, 5, 0 is 1, 1. and f of 0, 1, 2 is whatever the hell it is. Just have to think that one through. Yeah, that's all right. It can be whatever I want. 0, 1. Okay? So this is the classic question that your lecturer thinks is cool. Actually, your lecturer doesn't think it as cool as I think it is because I know how to do it, and your lecturer doesn't have my way of doing it, which is better. So there's this, and then you say find the standard matrix of f, or possibly even find the kernel of f, all right? Which means generally you find the standard matrix first and then find the kernel from there. So if you want to find the standard matrix, you need to find out what f of 1, 0, 0 and f of 0, 0, f of 0, 1, 0 and f of 0, 0, 1 are. So we already have the first column. The first column is 2, 3, because that's the correct one there. We now need to find the other two columns. So we need to find these two. Okay? So, great. So there is one way of trying to attack this, is to say, well, linear transformations means that if you do any linear combinations before, you can do the same linear combinations after and it will produce the correct answer. So I know, for example, that if I go this vector minus that vector, then the answer will be this answer minus that answer. So I can find the answer for f of 0, 5, 0. And then I can divide it by 5 to get the answer for 0, 1, 0. And that would be a perfectly reasonable approach. And this one here, once I've got 0, 1, 0, 1, 0, 0 and 0, 1, 0, well, I can just take off the one for 0, 1, 0 to produce this, the one that I want over here, and then divide by 2, which is fine, and that's perfectly reasonable. Okay? There is another way of doing this. We want to take these three vectors and to do some combination of them to produce these three vectors. Those three vectors. That's what we want to do. And that same combination of these inputs, we want to do that combination on the outputs and it will produce the answers that we want. Yeah? So, must find linear combinations of 1, 0, 0 and 1, 5, 0 and 0, 1, 2 to produce 0, 1, 0 and 0, 0, 1. And technically 1, 0, 0 as well, but we've already got that one. But just for completeness' sake. So linear combinations are just multiplying by stuff and adding stuff together. And we need to do the same combination on the outcomes, right? And do same linear combination on output vectors. Yep. And that will produce the answers that we want. Awesome. Well, row operations do linear combinations of rows. So if we just wrote everything as rows and did row operations, then we would get what we want. So row ops to do linear combinations. So let's have a look at this. So we know that we have 1, 0, 0 and it produces the answer 2, 3. And we know we have 1, 5, 0 and it produces the answer 1, 1. And we know we have 0, 1, 2 and it produces the answer 0, 1. And we want to do row operations on this until it produces 1, 0, 0, 0, 1, 0 and 0, 0, 1. And by the time we've done that, those same row operations will have been done on this bit, and I will have done the combinations that I need to do automatically because that's what row operations do. They do linear combinations. And so I just need to do row operations. Like that. And then I might switch these last two rows. Or if you had a calculator that was clever enough, you could do it in your calculator. I could have just divided that one by 5 and that would have produced the correct answer, wouldn't it?
Calculators that clever allowed the exam?
Sorry?
Calculators that clever allowed the exam?
I believe a graphics calculator of an ordinary type, not one that does algebra, is allowed. I won't do that. I'll divide that one by 5. You'll notice that these row operations are exactly what I described before, but I don't have to think so hard about them. So I'm going to do row 3 is row 3 minus row 2. 1 2/5 would be 7/5, and then I'll divide by 2. Yes, it is. As I said to the Maths 1A students half an hour ago, or an hour ago, the important thing about exams is to keep a clear head. So you should get a good night's sleep beforehand and not give 5 hours of seminars before you plan to do a row operation. So I did eat, just not enough. So this there is the outcome that 1, 0, 0 will produce that outcome. And 0, 1, 0 will produce that outcome, and 0, 0, 1 will produce that outcome. So therefore the standard matrix is 2, 3, minus 1/5, minus 2/5, 1/10, 7/10. Did I do it right? Magic, right? I love it. But I do have a feeling that the person reading your exam will probably go, where did they pull this from? And you should probably have some sort of explanation that goes, I'll do row operations on the rows because that does correct, because row operations is linear combinations and that's what I want to do. Something like that, so that the person who reading it knows you didn't just pull it out of the air. Yeah. There is actually other ways of solving this problem which are also mathematically just as awesome, but not in terms of the amount of time it takes to do them. All right, well that's everything I want to say about linear transformations off the top of my head. Does anyone have any questions about linear transformations? Yep?
Yeah, you said before we couldn't call it a null space of F,
Mm-hmm.
but it's written like pretty much in our notes, like in the definition.
Let me see. Where?
Like at the top of the page, yeah.
Ah. All right, apparently your lecturer thinks that you can write null space of a linear transformation. That's fine. Believe them. I think it's wrong, but then again, I'm a stickler for good grammar. But you definitely can't say the column space of a linear transformation. So, yeah, cool. You can say null space of F. Damn. It's more correct to say the kernel. Just to point out that actually ordinary functions have kernels as well. So y equals x squared has a kernel. It's just the ones that produce 0 as the outcome. And so what you used to think of as kernels, what you used to think of as the zeros is the kernel. Yes?
The column space is the space corresponding to the range of the matrix, the linear transformation. Is the row space then the space within the domain that of everything that doesn't get annihilated?
No. So you've asked about if the solution set, the null space is the kernel, and the column space is the range, what's the row space? Nothing. The row space doesn't represent anything physical at all. It might, but I don't think it's what you said. I'm fairly certain it doesn't represent anything. It would, of course, be the range of the inverse. No, not the inverse. Just ignore that entirely. Let me just think about that. The column space is the row space is the perp of the kernel. So the row space is the set of vectors that are perpendicular to the kernel. I'm fairly sure that's true. I could be wrong, but No, that's completely correct. So the row space is the vectors that are perpendicular to the kernel. So if your kernel is a line, then your row space will be perpendicular to that, and it will be a space as well. That's totally awesome. Wow. Okay. Yes?
Is there any way to quickly tell by just looking at it whether a function is a linear transformation or not? Is it just if it has squares in it, or
Pretty much. So that's a good question. You know, how to tell. How to tell if it's a linear transformation? The answer is, if you can rewrite it as a matrix, then it is. So, which means that each entry, so each coordinate in the outcome must be a linear combination of, x, y, z, however many of them there are. And then it is. And if it's not, then it's not, basically. So if there's squares, or if any of them are multiplied by each other, or there's divisions, or there's square roots, it's just not going to be. It has to be, each coordinate has to be a linear combination of the original variables, which means that you can rewrite it as a matrix. So if someone says, show that this is a linear transformation, you can very quickly go, I rewrite it as a matrix, therefore it is. Yep. That's right. So the thing that's in your lecturer's head is for showing that something's a linear transformation would be to get x, y, z and sub in cx, cy, cz and see if the answer, see if you can pull a c out of the answer. And the same with addition. Yeah. But if you want to look in advance and they have a list and say, which of these are linear transformations, and they don't want you to justify your answer, you can say, that one's not, it's got a square, that one's not, it's got a square root, that one's not, it's got some, yeah. So, yeah. Yes?
Is there an easy way of remembering the projection formula, the orthogonal projection formula?
I don't know. I've never had a problem with remembering it, so let me think about it.
I'm going to have to look it up because I can't remember it right now.
Yeah.
Just u v1 v1 plus u v2 v2 is the
Yeah.
plane, so on.
Let me just compositions of linear transformations. I'm going to talk about that first because technically yours is else, and I'd like to do all the other stuff in. I start recording again. So. All right, composition of linear transformations. Awesome. So composition of linear transformations is the same as composition of any other functions. You just do one of them and then the next one. And it's useful to think about it in terms of the before and after and then the next after. And generally they'll ask you what the matrix is of the composition. That's about it. So you might have f of x, y, z is something like that. And then you might have g, maybe I'll... You might have g of x, y, z, t is t plus x plus 2z, y, something like that. And then you'll be asked, what is g of f? So you might be asked, is it possible to do f of g? Okay, so f of g is undefined because the output from g, so f of g of a vector is f of g of a vector. Yep. And this outcome is a length 2 vector, and the f needs a length 3 vector to go in, and so this isn't actually defined. So not defined. And in terms of diagrams, we know that G starts in R4 and produces R2, and F starts in R3 and produces R4. And so since f starts in R3, we can't do G and then f, because it starts in a different place than that starts. But we can do f and then G, because f ends in R4 and G begins in R4. So G of f is defined because the answers from f are 4 and the questions from G are also 4. Okay? So this function therefore is we start in R4 or R3 and we go to R4 and that's f, and then we do G and it ends up in R2. And so G of f goes directly from R3 to R2. Okay? Awesome. And if you want to find the matrix for G of f, you just have to multiply the matrices of f and G together. So matrix for G of f is matrix for G times matrix for f. And so you'll just find the matrices of each of them, multiply them together, and that will be the answer, in the order that they're presented in the G of f. It has to be in the order that you write the G of f. Because the thing is that you do them on the left-hand side of your vector. So you've got a vector here, and you do a matrix here to do f, and then you do a matrix here in order to do G. And so they have to be multiplied in that order or it won't come out right. And the sizes will be wrong to multiply if you try and do them the wrong way, other way around anyway. Okay? Correct. So that's pretty much how it's done. And if you're asked for the kernel of G of f, then you could just get it from the matrix. I'm watching. But you do also have, some information. You know that R3 is going up to R4, so the most that the range of f can be is R3. And you're going therefore from, and so we've got a three-dimensional object here. Everything else, we're not going to produce it out of f, and that's going to produce an R2. So we're going to have to leave one dimension behind here. I mean, if I was just doing this, I have to leave 2 dimensions behind here. And if I was unlucky enough for the three-dimensional object here to land with that 2D thing inside it, then I would lose most of it and be left behind and only have a range of 1. So you know what options are possible for what the sizes of the ranges, dimensions of the range and everything can be. Yes?
Is there a fast way to go straight to the composition matrix without doing all the F and G matrices individually?
So I've just been asked, is there a fast way of going straight to the composition matrix without doing f and g individually? Yes, there is. Because you just need to find what G of f is of the standard basis. You see, the matrix for G of f will have as its first column G of f of 1, 0, 0, and as its second column G of f of 0, 0, 1. So you could just go, all right, well, f of 1, 0, 0 is 1, 0, 0, 0, and G of f of 1, 0, 0 is G of 1, 0, 0, 0, which is 1, 0. And then f of 0, 1, 0 is 0, 1, 1, 0. So G of f of 0, 1, 0 is G of 0, 1, 1, 0, which is, so we've got Z is, just looking at the formulas. T is 0, X is 0, Z, so 2, 1. And finally, F of 0, 0, 1 is 0, 0, 0, 0. So G of F of 0, 0, 0, 1, is G of 0, 0, 0, 0, which is, of course, 0, 0. And so therefore my standard matrix must be